Oh, well, as I say, before we broke, we looked at logarithms. The inverse of logarithms are our exponentials. So let's remind ourselves of the basic exponential curve. There it is, asymptotic on the left to the x-axis, and then it rises starts off shallow, hits 1, and then gets steeper and steeper. That's for a basic exponential where the base is greater than 1. If the base is in between 0 and 1, then it's a reflection in the y-axis. It does the opposite. It starts out here, it's infinity, comes down quite steeply to 1, and then gets shallower and shallower to the x-axis. But of course, if we play with negative indices, the red one there could also have a base between 0 and 1, but it could be a to the power of negative x. Because remember, the negative power means turn it upside down. So a half to the power of negative x would be the same as 2 to the power of positive x. So hence, it's the same graph as the red one. Which also means if the base was bigger than 1, but it was to the power of negative x, it would look like the blue curve. Because 2 to the power of negative x would be the same as a half to the power of x. So they're our basic ones. And of course, the one we're most interested in is e to the power of x. But e is around about 2.7. More about that in a sec. So domain, well, we can see it's all real x. It's a continuous graph. There's no breaks in it. The range is y is greater than 0. We cannot raise a number to a power and end up with a negative number. Not for a continuous curve anyway. Obviously, we could raise negative 2 to the power of 3 and end up with a negative 1. But you can't draw negative 2 to the power of x. You won't get a nice continuous curve. Because raise it to an even number, you'll get a positive. Raise it to an odd number, you get a negative. So it jumps around all over the place. Basically, it's very chaotic, all sorts of random points. So we're more interested in the natural base. E lines up with the natural logarithm that we looked at. So e to the power of x. E is another irrational number. It's much like pi, goes on forever. You can't write it exactly as a fraction. We don't know what it is exactly. But it is defined as this. The limit as n approaches infinity of 1 plus 1 on n, all to the power of n. Okay, so as you sub numbers in for n, the bigger the number is, the closer and closer you'll get to the precise value of e. It has a value, we just don't know exactly what it is. So say an approximation on your calculator, it looks like it repeats, but that's just because of the limit of your calculator screen. So it looks like, oh, look at that, 1828, 1828. But trust me, after that, the digits do change. So it doesn't just keep going 1828 all the way down. So e cubed on your calculator, well, again, you use your natural log button. Probably have to do inverse or shift depending on your calculator. And you could go, oh, well, e to the power of 3 is 20.086 to 3 decimal places and so on. All right, let's look at the important things. When we look at our new functions now, because we're interested in calculus, we want to know how do we differentiate it, how do we integrate it, things like that. So, it's the world's easiest derivative. E to the power of function x. You differentiate the power and you put that out front. And then it's just e and the power doesn't change. And that's where you've got to be careful, because remember with a polynomial, you get the power and bring it to the front and subtract 1. So the power changes. That's a polynomial. With an exponential, because the x is now in the power, it's not the base. Polynomial, x is the base. So when it's the power, you differentiate the power, that goes to the front, and then e2 and the power doesn't change. If it's not a natural logarithm, so it's some other base, you still do it exactly the same way, but you also multiply by the natural log of the base. And that's all to do with the change of base rule. Because basically what you're doing is you're changing it to a natural base so you can differentiating it, changing it back, and it comes up with something like that. But to save all that mucking around with the change of base, effectively all that happens is we multiply by the natural log of the base. This is the world's easiest question. E to the power of x, differentiate e to the power of x. You get e to the power of x. Because differentiate the power is x. Differentiate x, you get 1. So 1 goes to the front, times e, the power doesn't change. So that particular graph, that exponential graph that we saw, has a very interesting feature in that the y value is always the same as the slope. And that explains why it starts off shallow and gets very steep as you go along. So as the x values increase, the y value is going to change, but now the slope of the graph is the same as the y value, so it's getting steeper and steeper and steeper. E to the 5x then, differentiate 5x, you get 5. So we have 5e to the 5x. E to the 4x plus 3, differentiate 4x plus 3, 4e to the 4x plus 3. E to the x squared plus 3x plus 2, it doesn't matter what it is, differentiate the power. In this case, obviously, I'll put it in parentheses because it's all of that. 2x plus 3 is the derivative times e to the x squared plus 3x plus 2. We could have a question where we need to use the product rule, right? Because you've got two functions at x there. 3x squared, but you've also got e to the 4x. So write down the first, 3x squared. Diff the second. Let's say e to the 4x. Differentiate the power. That's 4, so I get 4e to the 4x plus. Write down the second, e to the 4x. Differentiate the first, differentiate 3x squared, 6x. So let's tidy that up a bit. Factorise. I tend to factorise these because usually when you've got a derivative, you're going to do something with it. It might be find stationary points. So if you've got to find stationary points, you've got to solve it equals 0. And when you solve it equals 0, you've got to factorise anyway. But of course, the interesting thing with this is the e to the 4x can never equal 0 anyway. So this one, if it was stationary points, well, the 2x plus 1, that could equal 0. We'd have one at x equals minus a half. And 6x, of course, could equal 0 as well. But the e to the 4x wouldn't produce a stationary point. Chain rule. Anarchy. Bring down the power. Okay, so the 7 comes to the front. Lower the power 6. Diff the inside. But inside, we've now got an exponential. So e to the 3x, differentiate, becomes 3e to the 3x. And just tidying that one up, there it is, 21e to the 3x, e to the x, 3x plus 2. Quotient rule. Okay. Square the bottom, e to the x plus 3 all squared. Write down the bottom, e to the x plus 3. Diff the top. The top, world's easiest derivative. Differentiate e to the x, you get e to the x. Minus, write down the top, e to the x. Diff the bottom. World's easiest derivative. Differentiate e to the x, you get e to the x. Now be real careful. It is so easy to make a silly mistake here and go e to the x times e to the x is e to the x squared. Of course it's not. Remember your index rules. Add the powers. It's e to the 2x, e to the 2x. So in that one I've got e to the 2x plus 3 to the x minus e to the 2x. So the e to the 2x's cancel out and I just have 3 e to the x on the top of that one. All right, let's put it in context, the question. We want to find the tangent to our exponential curve, e to the 2x plus 1. So it's our standard exponential curve. A little bit steeper because it's e to the 2x rather than e to the x. And it's shifted up 1. So what's the tangent to that curve at the point 1, e squared plus 1? So let's differentiate it. The derivative is 2e to the 2x. But remember, that is not the slope of the tangent. That is the formula that allows you to find the slope of the tangent. So we want at the point x equals 1. And when x equals 1, the derivative is 2e squared. So I have a slope, I have a point. It looks a bit messy because of all the e's. Remember, e is just a number. So it's y minus e squared plus 1 equals 2e squared x minus 1. Expand out, group together. So the constant number in this case is e squared or minus e squared plus 1 there. One of the big mistakes people make with this sort of question is they get to 2e to the 2x and they sub that in as the slope. They don't actually go and find the slope. And so you see an answer like y minus e squared plus 1 plus equals 2e to the 2x times x minus 1. Very common mistake. So remember, the derivative is the formula that allows you to find the slope. It's not actually the slope. You've got to substitute in to work out the slope. There we go. Mere mortals would shudder and cry and run away. 4 to the power of x squared, but us super mathematicians, not a problem. We'll do it just as normal. Differentiate the power, differentiate x squared. We get 2x. And the other difference is, well, we'll multiply this one by the natural log of the base, the natural log of 4. I tend to write log Remember, you could write ln for natural log. A lot of people do that as well. Oh, hang on. What's that doing here? Y equals log x. We already know the answer to that. We did that back in logs. What's this doing in exponentials? Let me show you how we get it. Because now that I know they're the inverse of each other, if y is the log of x, x therefore is equal to e to the power of y. Okay. I could differentiate x with respect to y. Well, e to the power of y, differentiate that, that's the world's easiest derivative. So it's e to the power of y. But that's dx dy. I want dy dx. So I'll turn it upside down. So there's the derivative, 1 on e to the y. But that's not how we saw it, of course, because x is equal to e to the power of y. And so we end up with derivative 1 on x. And so that's where our idea of derivative on function for logarithms came from. It's actually differentiating exponentials and turning it back the other way. All right, there's a couple of exercises to get us going. Let's see how we go there.